Cool. 493 reverse pairs. Given an array nums, we call I sub j an important reverse pair if I is less than j and num sub I is greater than 2 times num sub j. Okay. You need to return the number of important reverse pairs in a given array. Okay. That's easy to say at least. The other one had like 5 pages of instructions. Okay, so I is less than j, meaning if in this case 3 and 1 is 1, and also the other 3 and 1 is 1 because it's bigger strictly too. Okay. So right off the bat, the thing I'm thinking of is a couple of strategies maybe. One is divide and conquer. Like some kind of recursion stuff. N is 50,000, so you can't do n square. But if I could do some kind of n log n type merge sort type thing with counting inversions, because this is almost like counting inversions, and then you just merge sort the number of. Yeah, I mean, I think maybe that's right. It's just like inversions, but with 2 times, and then when you're on the merge step, you just have to do certain things and make sure you pop the things in a easy way, and then sort afterwards. Is that good? Yeah, okay. Let me try that approach then. It's an interesting inversion. Okay, so yeah. Return 0, I suppose. Otherwise, okay. Well, now we also want the array, so I guess we need a helper. Was hoping to do it kind of cool recursively or something. Kind of still can actually, but now you need a way to merge. Okay, fine. Some nums and so we return a tuple where the second is to count. Okay. So this returns left and this is returns right. So then count is just equal to left of 1 plus right of 1, and then we return the merged nums with count. I have to do the merging now, and then let's actually just do it this way. It should be more Pythonic while I can. So let's just do. Why do I have an M? New nums. Okay. So that means while let's just end, and then we could just do the other cases later. Okay. So now this is just standard merge sort, I think. Okay. If I mean we have to resort it afterwards, but I think we could just at least dump the numbers in a bit. Yeah. Actually, doesn't we don't even need to sort it actually. No, we should sort it. So add it'll be like a weird fact. I forget the number, but um, yeah, okay. If left of 0 is so the left, if this is greater than 2 times right of 0, then we count. No, we count more than that. That means, let's think about this. Do we want it? Maybe we don't want it in the right order. Maybe we want to reverse. Oh, and this actually should be recursive anyway. Oops. Oops. So now we want okay, what happens when this is the case? That means this is because this is smaller, so it's oh, I think that's right actually. That means because left is smallest, this is going to be the size of left because if this number is smaller than the smallest number of left, then it's smaller than everything else that's in left and left. Okay, that's just a mouthful. Left and left. Okay, and then also we pop. What do we pop? I guess we pop the right, right? I guess these should be decks. Okay. Okay, let's just call index. Let's not do it this fancy way. Let's try to be. I'm just usually I don't care about that much about space, but I think I'm with 50k as an n. I worry a little bit about. I do worry a little bit about space usage, so I'm going to just use the pointer. Also, that's wrong. Give me a second. If this is the case, then what's so that's then of left minus left index, maybe minus 1. Don't know them. Maybe this is off by 1 though. But then now we write index plus plus. Else you start append count. Oh no, not count. Why am I saying count? The right number. Gotta do it before, obviously. Otherwise we just do it to the left. And then that's it. I guess I don't really need to do this yet. I think new nums is because we're going to sort it anyway. It's already not going to be sorted because it's only 2 times whatever. So then in that case, new nums is equal to left plus right, and then sort it. Okay. Well, I need a base case. That would be nice, right? If n is 0 to 0, return 0, or I guess just less than or equal to 1. return 0. Maybe that's okay. Int object. Do I not return everything? Oh, well, yeah, obviously. There's num0. Okay, well, okay, let's just print stuff out. Yeah, maybe there's an off by 1 or something. Because that's n. That's fair. That's fair. We don't do the entire array. Why do we never return the entire array? Maybe something Pythonic. No, I mean we do. Well, I don't know what. Let's do one where, just for illustration, that they're distinct numbers for debugging. Yeah, so it only takes left. That's what I was suspecting. That's why I wanted to change up the numbers. Though this is the right answer, but that's just by accident. What happened to the right? Do I not recurse right? No, I do recurse to the right. Oh. Oh, I'm just being dumb. Because I don't. I said I would do it, but I didn't. But when this is stops being true, though this doesn't make sense for here. Alright. I mean, I definitely don't handle everything, but that's for sanity check. Let's print this for a second. Maybe the plus is not right. I thought that's right though. Oh, Why is the right one? What? What's the input and what's the left and the right? Where am I getting that from? That's weird. Yeah, okay. But why is the left and the why is there only one element? Am I messing that up? Clearly, but am I off by 1? Maybe this is off by 1. I'm always really bad at inclusive and exclusive. That's probably right. Should also debug that faster if that's the case. But okay. Still unintentionally right. So let's give it the example case. Actually, let me give it another case. Maybe I don't need to print this. Okay. Oh, I actually got both of them right. I thought there's an edge case. There is definitely an edge case where I don't handle. So this is also another case of being right by accident. So I think I could do a big case of like, which is also unfortunate when that happens to you. But that's why you have to stay vigilant, because sometimes just because your past cases doesn't mean it's right. Because I don't handle what happens after this while loop, and you should. And I think you have to times it by what the. Okay, well, because I think what you need to do is count to if you have left element what happens if you have left elements left or right elements left? Well, you append it and that's fine. Does that mean anything? No, I guess it just happens to be right in the sense that well, usually when you need to sort, you would put it in the back of the array, but that also means that in this case, it means that this condition will no longer be true no matter what. So, right, is that right? Because there's no numbers left. Because that means the number on the right is times 2 is bigger than all the numbers on the left, which is there's none left. And in the other direction, we already did all the math. So okay, so maybe that's right. Huh. It's always fun to think about. Let's hope that this doesn't time out, or that I have to do this smarter maybe. But okay. This could be faster because I just used a naive sort. You could imagine. So this adds another maybe log n factor or sum of log n's. That's actually not. I forget how the math goes. But you could just actually put this in the same loop, and then that would make sure that's n log n. So mine is definitely a little bit slower though. Though still faster than 70%, I suppose. 1.7 seconds is a little slow though. 20 meg. I use more memory. Why do I use more memory? I guess I construct a new array every time on the sort. So maybe if you do it in place, maybe that's okay. That would have made the memory much lower. That's fine. So yeah, so in theory, if you do it correctly and less lazy, this is n log n and space. You could do, with merge sort, you could. Well, no, it'll be tricky to do in place actually. There are ways to do it, but it's not really standard. But yeah, so of n extra space, or I guess in this case n log n extra space because they're n of n depth. That's the way I did it, maybe. Yeah, I guess you can make it all of n space if you're a little smarter about it. But yeah, but that's kind of how I. Cute problem. I mean, I think one of the problems that I do like, as an interviewer when I give interviews is just problems that you have all the tools for. You should have all the tools for. All the basic functions, meaning sortings, searching. What are the other ones? Depth first search, breadth first search. Well, when I say searching, I guess I meant binary, but like those kind of problems. And this one, it's kind of like, hey, do you know merge sort? Without actually be like, oh, just implement merge sort. And it's kind of, it gets around. I mean, some people may still hate it anyway, but definitely people were like, you'll get people who are like, why would I ever need to know how to implement merge sort and then do it that way, right? And I think in this case, it's not. I think for me, as just in general, not necessarily for interviews, it's not that you need to know merge sort. It's that from merge sort, you learn a lesson about divide and conquer in a consistent way, and then the analysis of that, and kind of like like recursion in a way as well to some degree. Though you don't need to, but anyway. So I think that's in theory the lesson to be learning from a merge sort. So then, and when you learn that lesson, then you can reapply it in different cases, like in this one. Though I will say that that I have a sort of a thing on this one because I do recognize this problem as like a variation of something called an inversion. And inversion is just measures how unsorted a problem, a statement, an array is. And that's just basically this thing. It's the same definition except for about the 2 times numbers of j, and that would kind of give you the inversionness. And merge sort is, and you guys should do this with quick sort as well. But merge sort is one of the straight or more that you guarantee is n log n versus like in a really bad case, you could do you could use quick sort to count the number of inversions and in a similar way, but you could fall into n square, an n square worst case, right? And that's also something that they teach in school. Though in real world, quick sort is very hard to be n squared because you could always mix up your inputs by like just randomly sorted once before running the algorithm. Very high probability of n log n, but you can't do that for counting inversions, right? So well, it's not. Maybe I shouldn't say that. I don't know, but I don't think, at least off my head. So yeah, so that's kind of this problem. I recommend it. It's a little. I mean, it's implement merge sort, so and that's something that I do recommend. So yeah, and I do feel happy that I got it done.